Okay, thank you for tuning in. If you're watching this video, you're probably a student in Math 253 with Professor Lapuz. Either that or you're really bored, the channel surfing isn't very good. So if that's the case, stay tuned, this is really interesting stuff. But the question is, do these two planes represented with these two expressions intersect? They do. And if they do, what's the angle of intersection and what's an expression for the line of intersection? So those are the two questions. We're given a couple of planes. The question is, what's the angle of intersection and the line of intersection? How do you get there? And along the way, there are a lot of questions that need to be answered in order to drum up the necessary facts, in order to do the computations to prove the angle and line of intersection. There's some cross products and dot products that need to be determined. There's some direction vectors, 3 of them that need to be determined. There are 3 magnitudes that need to be determined. And most annoyingly, there is the computation of a point on the line of intersection that needs to be determined. So that's the question. Those are the necessary facts in order to answer those questions. And here's kind of a roadmap for how you get there. The process by which I answered these questions was, first, take a look at the expressions. And from a visual inspection, the dot product can be determined, which tells you that these two planes intersect at a right angle. The dot product is 5 times 1 minus 3 times 4, which is 12, so that's -7, plus 7 is 0. The dot product is 0. These two planes probably intersect at a right angle, and there's some additional evidence that can be drummed up in order to prove it, including the inverse cosine of the dot product divided by the product of the magnitude of these two direction vectors, and a visual inspection of the graphs in Desmos and MATLAB. So after looking at the graphs, there are 3 direction vectors whose magnitude needs to be determined. This one, and the magnitude of the cross product. Most annoyingly, a point on the line of intersection must be established, that in order to complete the equation for the line of intersection. So the last thing I'll explain to you here before I start a screen recording of a MATLAB session is walk you through the process of determining a point on the line of intersection. This is the same as homework 2.5 question 21, which I think made a lot of people in class kind of crazy. Sometimes I think Professor Lapuz gets a certain amount of sadistic pleasure out of driving us nuts trying to figure out some of these math problems, and computing a point of intersection, a point on the line of intersection between these two planes was a little bit of a chore. But it's accomplished using a little bit of substitution, back substitution, and system of equations. So first, assume that z is equal to 0, and that's a valid assumption if you look at the graphs of the planes. They both have a point where the line of intersection has a z value of 0. So this is a valid assumption based on inspecting the graphs. So if z is equal to 0, this expression reduces to 5x minus 3y is 4, and this expression reduces to x plus 4y is equal to 1. Second expression times 4 allows elimination of the x terms. So we're down to one variable, 23y is equal to 1, or y is equal to 1 over 23. We've now got a z term and a y term. Question is, what's the x term? 5x plus 20y, 20 times 1 over 23 is equal to 5. The result is this really ugly piece of algebra, which simplifies to this equally ugly piece of algebra, which results in x being equal to 19 over 23. So now I think we have one point that is on the line of intersection between these two planes, and The question is, did I do it right? So take these three terms, plug them back into one of the two original expressions, and see if it results in a valid expression. So x plus 4y plus 7z is equal to 1, or 19 over 23 plus 4 times 1 over 23 plus 0, is that equal to 1? And in fact, it is. So that proves that these three values represent a point on the line of intersection, and it's one of two little fact items that are needed in order to compute an expression for the line of intersection. These are the x0, y0, and z0 values for the line of intersection. The ABC values for the line of intersection are the coefficients of the direction vector that is the cross product of these two direction vectors. So that is everything I want to explain to you on the whiteboard about how to follow these steps in order to answer these questions. And from here, I'm going to turn on a screen recording and show you how in Desmos and MATLAB to graph those two planes, and how to use MATLAB to do these computations of the magnitude of a vector, the cross product of two vectors, the dot product of two vectors, and the inverse cosine of that expression. So thank you for watching. In the next few minutes, you'll see three graphs of the two planes, some evidence from Desmos suggesting they intersect at right angles, and on CalcPlot 3D, you'll see the line of intersection and that point on the line of intersection that was previously computed. What you see is the two planes graphed in Desmos, and moving the graph around, it sure looks like they intersect at right angles if you look at the two planes just about head on. You can also see that the line of intersection cuts through the xy plane. So the previous assumption about z equals to 0 in computing the point on the line of intersection seems to be a valid assumption. Here's the graph in CalcPlot. It's easier to see the line of intersection and the point previously computed that sits on the line of intersection. More on that in a minute. Here's a graph of the plane in MATLAB. It's not as easy as CalcPlot, and from this picture, they sure don't look like they meet at right angles. This is what MATLAB looks like when first started. Over on the right is a command window. You can type in commands and computations just like you're punching in numbers to a TI-84 calculator. On the left are a couple of scripts. This first one is the code to generate the graph of those two planes. There's not a lot of it, but it took me a long time to figure it out. In the middle window here, titled Workspace, you can see variables representing the results of calculations. If you've done this problem already, the numbers should look a little bit familiar. More on that in a minute. Looking at the script for computing the variables needed to answer these questions, the first two commands that say direction vector equals, they just make direction vectors from the XYZ coefficients of the two planes. I can type these commands into the command window, I could copy and paste them over, or I can just run this script, all producing the same result. MATLAB has a norm function that returns the magnitude of a vector. MATLAB has a dot function that computes the dot product of two vectors equal to 0 in this case of the two direction vectors in this problem. MATLAB has a cross function that returns the cross product of two vectors, and those values are 24, 25, and negative 23 respectively, seen again here. And these x, y, and z coefficients are the a, b, c values in the expression of the line of intersection. And finally, MATLAB has an ACOSD function, inverse cosine in degrees, in this case returning the inverse cosine of an expression that is the dot product of the two direction vectors divided by the product of the magnitude of the two vectors. In this case, that result is 90 degrees, further proving that the two planes intersect at 90 degrees. So, kind of by way of summary, this should answer all the questions about the angle and line of intersection of the two planes. They intersect at a right angle, and the line of intersection is this parametric equation here, represented with this blue line on the graph. After looking at the graphs in MATLAB, CalcPlot, and Desmos, we computed the coordinates of that line of point on the line of intersection using substitution, elimination, and a lot of aggravation and frustration. Those numbers are the x sub 0, y sub 0, and z sub 0 values in the equation of the line of intersection. We prove the angle of intersection twice, first by computing the dot product of the two direction vectors of the planes, which is equal to 0, and then computing the inverse cosine of the dot product divided by the product of the magnitude of the two vectors, which is 90 degrees. We computed the x, y, and z coefficients of the line of intersection by computing the cross product of the direction vectors of the two graphs. And those numbers are 25, 34, and negative 23. And finally, we plotted all of this using CalcPlot 3D. You can see from the picture that the planes intersect. The parametric equation of the line of intersection is shown, and it is light blue on the graph. That point on the line of intersection, 19 over 23, 1 over 23, and 0 is the big red dot in the middle of the graph. So I hope all of this is helpful and interesting. If you got questions or need more information, please let me know. Thank you for watching.